We are continuing with chapter 2 now in our 235 course. The goals of this chapter are um, to identify a polar covalent bond, be able to figure out the formal charge of an atom or a molecule, able to draw resonance structures, identify Lowry-Bronsted acids and bases, predict the strength as well as the direction of this acid-base reaction, identify Lewis acids and bases, and finally, understanding of non-covalent interactions between molecules. So this part of the video will discuss about polar covalent bonds. Now, before we move to polar covalent bonds, let's quickly recall the property called as electronegativity, which we must have learned in general chemistry. Electronegativity is the intrinsic ability of an atom to attract the shared pair of electrons in a covalent bond. Okay, if the electronegativity difference between the two atoms is exactly the same, then the pair of electrons are shared equally between the two atoms. However, if one of the elements is more electronegative than the other, then the electrons are shifted more towards the more electronegative element. Okay, so this is a arbitrary scale of electronegativity. As you can see here, fluorine is the most electronegative element and cesium is the least electronegative element. So metals on the left side of the periodic table, they have weak ability to attract electrons, whereas non-metals here like halogens, oxygen, nitrogen, etc., they have higher electronegativities. That means they have more tendency to attract electrons towards itself. Okay, and then carbon has a value of 2.5 as shown in this table here. As I was saying in the beginning, that if the electrons are shared equally between the two atoms, that happens when the electronegativity of the two atoms is exactly the same. Okay, so that would be a case of pure covalent bond. Now, if the electronegativity of one of the elements is much higher than the other, then the electrons are completely transferred to the more electronegative element, and then that results in the formation of a ionic bond. Okay, so examples of these would be like hydrogen atom, right? So one pair of electron, which is shared equally between the two hydrogen atoms, resulting in the formation of the hydrogen molecule. Or in this case, where we have an ionic bond, a good example of this is like NaCl, where sodium loses the electron, chlorine gains the electron, and you get the ionic compound sodium chloride. However, there are a large number of compounds which lie in between these two extremities, and they fall under the category of polar covalent compounds. And polar covalent compounds are those compounds which contain polar covalent bonds. And what are polar covalent bonds? As shown in this example, if one of the elements is more electronegative than the other, then it has a tendency to pull the shared pair of electrons towards itself, thus getting a partial negative charge, which is represented by delta minus, and the element which is lower in electronegativity gets a partial positive charge. Okay? So the electron distribution is not symmetrical. One atom has more tendency to gain the electrons. So this type of bond is called as a polar covalent bond. Now, how will we know whether a bond is polar covalent or not? So for that, we will use a simple scale. That means from the table, you can look up at the electronegativities, and if the difference in electronegativity between the two atoms that form the covalent bond lies in this range, 0.5 to 2, then that would result in a polar covalent bond. If the difference in electronegativity is less than 0.5, it will be a non-polar covalent bond. For example, CH bonds. Okay, CH bonds are non-polar covalent bonds because the difference in electronegativity between these two atoms is less than 0.5. A case of ionic bond would be where the difference will be of electronegativity between the two atoms is greater than 2. Okay, so this particular video, we are going to talk about polar covalent bonds and how to figure out whether a compound is polar or not. Now this phenomena is also called as inductive effect, where the shifting of electrons happens in a bond with response to electronegativity of nearby atoms. Several times you will see in your textbook this kind of a picture drawn. This is called as an electrostatic potential map. Here, the electron-rich areas are represented as red color, and the electron-poor areas are represented by this greenish-blue color. Now, there are two examples in this slide. One is that of methanol, and the other is that of methyl lithium. In one case, the carbon is less electronegative than the atom to which it is bonded, which is oxygen here. The difference in electronegativity between the two atoms is 1. Therefore, this bond can be considered to be a polar covalent bond. Okay. On the other hand, this here we have a carbon-lithium bond. Now here carbon is more electronegative than lithium. Therefore, this bond will also be a polar covalent bond. The difference in electronegativity is 1.5, and the carbon-lithium bond is considered to be polar covalent. Okay. Now, if you notice, we have a crossed arrow drawn in both the cases. This crossed arrow indicates the direction of, or indicates the more electronegative element. I'm sorry, let me say that again. So this crossed arrow is drawn in such a way that the head of the arrow lies to the more electronegative element. So here, since the more electronegative element between these two is carbon, so the head of the arrow lies in this manner. Okay, I can show you another example here. So say if I have HF, right? You can look up at the table of electronegativities to see whether this bond is polar covalent or not. So fluorine being the most electronegative element, this bond is polar covalent. And how will you draw the direction of polarity? It will be always from a positive end to the more electronegative end. Okay, so the head of the arrow lies towards the more electronegative element, which is fluorine here. Okay. Now we use this term dipole moment in order to measure the polarity. Okay, so it is a measure of polarity of a covalent bond. So higher the value of dipole moment, more would be the polar nature of the compound. Okay, so for example, here we have a, so how do we measure this, right? We have to use the formula Q times R, and it is represented as mu, okay, and it's written as mu, okay, it's mu, okay, this symbol here. Now that is calculated if you know the charge of on either of the atom, or the product of the charge Q on either atom of a polar bond times the distance between the two nuclei. Okay, so you have to take the multiplication of the charge times the distance, and that will give you this mu value. Here in case of chloromethane, the mu value is 4.80 D. D is the unit, divided, and it is pretty large, which means that this molecule is kind of polar in nature. Okay. You won't be asked to calculate dipole moment. However, if you are given the magnitude of dipole moment, okay, if you're given the magnitude of dipole moment, like in this case, then you should be able to tell which one is more polar and which one is less polar. So the higher the value of dipole moment, more polar the compound is. So here again, if you see, the direction of the arrow represents the overall polarity, or the direction of the polarity of the molecule. Okay, so now dipole moments are actually vector quantities. Okay, that means they not only have a magnitude, but they also have a direction associated with it. So in this case, the overall direction of polarity is this manner, because you can see that the lone pairs of electrons on the oxygen atom are shown here. In case of methanol, again, we have a polar covalent bond, and the direction of polarity is in this way. In ammonia, the direction of polarity is again this way, due to the presence of this lone pair of electrons. Okay, so all these three molecules contain polar covalent bonds, and that, as you can see, they do have dipole moment values. Now in this table, if you look, there are molecules which have a value of dipole moment, and higher the value, more polar the compound is, right? But there are some molecules here which have a zero dipole moment. Okay, so let's talk about when molecules can have a zero dipole moment. Okay, so the easiest way to look at it is that if the molecule has no polar covalent bond, right, then the molecule will have a dipole moment equal to 0. So for example, in case of methane, ethane, and benzene, the they all have only carbon-hydrogen bonds or carbon-carbon bonds, right? So in all the three cases here, they do not have any polar covalent bonds. Okay, remember that to have a polar covalent bond, the difference in electronegativity between the atoms which form the bond should be between 0.5 to 2. And in this case, that does not happen, and therefore these three molecules here are having a zero dipole moment. Let's take the example of carbon dioxide. Now in carbon dioxide, it's made up of carbon-oxygen bonds, and you know that carbon has an electronegativity value equal to 2.5, oxygen has an electronegativity value equal to 3.5, and the difference between them is equal to 1. That means it does contain polar covalent bonds. Then why is it the dipole moment equal to 0? Okay, so again recall that dipole moments have vector quantities. They not only have a magnitude, but they also have direction. Now in this case, there are two carbon-oxygen bonds, and you can see that the direction of dipole moment is equal and opposite to each other. As a result of which the dipoles cancel, and overall the molecule has zero dipole moment. Okay, so you can see this picture here again, where the dipole moments are equal and opposite, they cancel, and therefore the dipole moment is equal to 0. Let's try to solve some